So consider a differential equation du dt equal to f of u. Okay, and it has been actually through a lot of work even before Lorenz's time that if you linearize the equation, okay, if you solve a differential equation that governs the perturbation of a small perturbation epsilon times v, right? So if u is a solution that satisfies the equation, and suppose a different equation, a different solution satisfies the same equation, and the different solution is a small perturbation on top of u, then it can be shown that by actually Lyapunov is a multiplicative ergodic theorem that the v, the small perturbation, follows an exponential trajectory. So lambda, when it's positive, this perturbation exponentially diverges, exponentially grow, or when lambda is negative, this perturbation would exponentially converge to zero, exponentially decay. And for different perturbations, we have a discrete set of lambdas, discrete set of possible lambdas for every system, similar to like a discrete eigenvalues of a linear operator. And this discrete set of exponents are called Lyapunov exponents. The Lyapunov exponents of a dynamical system or ordinary differential equation can be used to classify what type of system it is. When all the Lyapunov exponents are negative, any perturbation to the system is going to die down to zero, it's going to decay to zero. That corresponds for an autonomous dynamical system, autonomous ODE, that corresponds to a steady state solution, right? I mean, if we look at the flow field, that corresponds to a steady state flow field because any perturbation upon the stable, steady flow field would die down to zero. When all the lambdas, all the Lyapunov exponents are negative except for one zero Lyapunov exponent, that actually corresponds to a periodic solution. That's like a periodic vortex shedding, right, over a black body at the low Reynolds numbers. The periodic solutions has 1, 0 Lyapunov exponent because there is one particular type of perturbation, a perturbation in the time evolution direction, right? So if V is exactly du dt, then that perturbation would never die down, right? If you perturb the flow such that you are one time step ahead, then the perturbed flow would always be one time step ahead. So that corresponds to a zero exponent. The perturbation would stay roughly a constant over a long time. Of course, we are interested in the chaotic type of dynamical systems where there exists at least one positive Lyapunov exponent. And the positive Lyapunov exponent means that there exists some perturbation, okay, such that if you perturb in that direction, the perturbation would grow exponentially. And of course, if you make a random perturbation, there is very likely at least some component of that random perturbation is in the direction of this positive v, right? Of this v with positive lambda. And as a result, almost all perturbations is going to lead to exponential divergence from the unperturbed trajectory. So that's the chaotic systems we are interested in. That's the same as what we see in weather patterns and in the Lorentz system modeling convection. These kind of chaotic systems are everywhere. For example, in numerical simulations of unsteady flows, even two-dimensional laminar flows, we observe chaotic dynamics. For example, in this vortex shedding over an airfoil, the Reynolds number is actually pretty low, it's 2000. And you can observe one definite positive Lyapunov exponent. So here, what I'm showing is the time evolution of different modes of perturbations. And the y-axis is the magnitude, is the L2 norm of these perturbations. And you can see one definite exponential growth that corresponds to the positive Lyapunov exponents. You can also see many negative ones, and some of them are intermediate, right? If you have to compute it for much longer times to determine if they are really positive or negative. By the way, if you have any questions, please interrupt me. I would rather answer them during the presentation rather than waiting to the end. Any questions? All right. A similar flow field for internal flows. Again, this is two-dimensional laminar flow fields, and in this case, we have more than 10 positive Lyapunov exponents. So essentially, there are 10 different types of perturbations that leads to different rate of growth in the linearized solution. Okay, so these are really positive answers to the question, can a butterfly in Brazil cause a tornado in Texas, or can a tiny perturbation cause a big change in the solution later on? The answer is positive both for the weather and for unsteady flow.